Welcome back, everybody. We are very happy to have Professor Mina Aganagic from UC Berkeley, and she's going to tell us about node categorification from geometry and string theory.
Okay, I'm extremely happy to be here to help Andre and Pasha turn 50. And so this work is about, this talk is about a paper that's hopefully to appear soon with Andre. And Andre knows I'm on his case, so I'll get it done even on his birthday. All right, so what I'll do is I'll describe two geometric approaches to the node categorification problem. Well, one should fundamentally view them as coming out of string theory. However, this is probably giving string theory a little bit too much credit. Really, to extract it from string theory required a work of Andre with his very many collaborators over the years, Roman, Rukavnikov, Devesh, Nikita, Andrei Smirnov, and so forth. Well, in the spirit of collaboration, this is Andre, of course, has had very many collaborators, and for an ordinary person, he's extraordinary in very many ways. But for an ordinary person who's turned 50, you just say, well, he turned 50. For a vain person, you could say, well, he turned 25 twice. But for Andre and Pasha, they turned 100 together. Okay, so as you'll see, one of the approaches that we'll derive has the same flavor as that of Kamnitzer and Kautis. The other approach is a relative of the approach of Seidel and Smith for SL2. The relation between them will turn out to be a version of two-dimensional mirror symmetry. Now, it turns out that there is a third approach to the same problem due to witness. And it has, in fact, the same string theory origin. So what I hope to convey is a sort of a unified approach to the node categorification problem that emerges from string theory. Okay, so to begin with, let's recall some very well-known aspects of node invariance. So to get a quantum invariant of a link, one starts with a Lie algebra, which will denote LG for Langlands, and you'll see why later, and a coloring of his strands by representations of LG. I should say, while Pasha is not part of this work, his wonderful book has been my constant companion for the last couple of years. So I know in a way he's here as well. All right, so.
So you mean book was Fred and
that's right, and that's right.
Okay.
Exactly. So the link invariant, in addition to the choice of a group and its representations, depends on one parameter Q. So Witten showed, of course, in his famous paper from '89, that underlying quantum link invariance is Chern-Simons theory with gauge group based on LG, and effective Chern-Simons level kappa related to Q. Now, in the very same paper, he also showed that underlying Chern-Simons theory is a two-dimensional conformal field theory with affine Lie algebra symmetry associated to LG at level kappa. So start with a space of conformal blocks of LG hat on a Riemann surface with punctures. We'll eventually be interested in invariants of nodes or links in R3 or in S3. So for that, we will take the Riemann surface to be a complex plane with punctures, or equivalently an infinite punctured cylinder. And it's actually the second view that I'll take for this part, for this talk. So the conformal blocks are correlators of chiral vertex operators on the Riemann surface. So the punctures at 0 at infinity are special. We'll take them to be labeled by a pair of highest weight vectors of Riemann modular representations of the algebra. To to punctures at finite points will associate chiral vertex operators labeled by finite dimensional representations of the Lie algebra. They act as intertwiners between pairs of Riemann modular representations. And so then to get the conformal blocks, you sew the chiral vertex operators together. In doing so, there are choices of intermediate Riemann modular representations you get to make. So you in fact get different conformal blocks, in fact a whole space of conformal blocks. So this notation hides that. So the space of conformal blocks on the Riemann surface with punctures is, as we can show, the Hilbert space after Simon's theory on the Riemann surface times time, where the strands are colored by representations associated with punctures. So to Simon's path integral on the Riemann surface times an interval in presence of a braid gives a corresponding quantum braid invariant. So this braid invariant is a matrix that transports the space of conformal blocks along the braid. Now, to describe that transport, instead of characterizing conformal blocks in terms of vertex operators and sewing, it's better to think of them as solutions to a differential equation. The equation they solve is the Aganagic logical equation, as Aganagic logical showed in 84. It's a regular differential equation as long as the punctures on the Riemann surface are distinct. So the quantum braid invariant is the monodromy matrix, so the Aganagic logical equation along the path in the parameter space corresponding to the braid. The parameters that you vary are positions of vertex operators on the Riemann surface. So the monodromy problem of the Aganagic logical equation was solved by Dreamfeld and Kono, and they showed that monodromy matrices are given in terms of R matrices of the UQLG quantum group. Yep.
Actually, this is trigonometric one. That was proven by Pasha.
No.
It's trigonometric. You have a paper, the monodromy trigonometric.
Yeah, but it's equivalent.
So in conformal field theory, it's the same, right? So I think you.
Except that your formula for Q is a little different from what we have. So in the book for Q is e to the pi I divided by.
It is 2 pi I over kappa.
But actually.
And there's just with the shift, right?
No, for simply Lacy algebras it is e to the pi I over kappa rather than 2 pi.
Yeah. So there's a question whether Q or Q to a half and so forth. So yeah. Physicists always have half integer powers of Q. So okay. Now, so anyway, the action of monodromies turns the space of conformal blocks into a module for the quantum group. In the representation, which in the tensor product representation, so we'll view rho as a representation of UQ of LG, and not of LG here, but we'll denote them by the same letter. So I won't change that. Anyway, so the thing that will be important is that the monodromy acts irreducibly only in the subspace of fixed weight. And the weight is fixed by the difference of the weights of the Riemann module at the two ends. So the way to think about it really is to pick the weight of one Riemann module and to pick a weight in the subspace, and then this fixes this guy.
Well, I'm not sure it's reducible always.
Huh?
For any Lie algebra, I don't think.
Oh no, it breaks up into blocks. If you don't on this space, it acts perfectly reducibly, right? Otherwise, it does not mix up different weight spaces.
No, but even if you fix a weight space, when it will be not obvious, but sometimes it's still reducible. What is that?
It can still be reducible.
Right.
That's a different thing.
For non-trivial reasons.
Okay. Now, what's it? Anyway, so what's important is another thing thing that you get is that this gives you a perspective of quantum invariance of not just braids, but also knots and links. So you can represent any link as a closure of some braid, simply by cutting off the top and the bottom. The corresponding quantum link invariant is a matrix element of the braiding matrix between a pair of conformal blocks, like this. The pair of conformal blocks that pick out which matrix element you're considering, the top and the bottom of the picture. How do you close off the braid into a link invariant? So, in general, you can consider arbitrary matrix elements, but if you want to get knot and link invariant, you need specific matrix elements. Those matrix elements that describe pairwise fusing of vertex operators into copies of trivial representation. So what this means is that, well, if you want to describe knot and link invariants, you want to pick a subspace of weight 0, because you want to fuse up everything. All right. Now, to categorify quantum link invariants, one would like to associate to a space of conformal blocks at a fixed time slice a bigraded category, and to each specific conformal block an object of that category. To braids, you'd like to associate functors between the categories corresponding to the top and bottom. And ideally, you'd want to do it in such a way that upon decategorification, you recover the quantum link invariance you were after. You were aimed to categorify. Right? That's the now. So one typically proceeds by coming up with a category, and then guessing a category, if you wish. And then you have to work to prove that decategorification gives you the link invariance you were after. You wanted to categorify. Now, in two of the approaches that I'll describe, to some extent the third one as well, but it's harder to see, the second step is automatic. The second, you will be guaranteed at the outset that decategorification gives you the quantum link invariance. Okay. So you know at the outset that your category does the job. So the starting point for us will be a geometric realization of conformal blocks that comes from supersymmetric quantum field theory and from string theory. So we'll eventually find not one, but two such interpretations of conformal blocks. But to explain how they come about, it's useful to ask a slightly different question first. In the end, one doesn't have to take this detour, but let's do it anyhow. So, namely, we'll first ask for a geometric interpretation of Q conformal blocks of the quantum affine algebra that is a Q deformation of the affine Lie algebra associated to algebra. So these Q conformal blocks, deformations of conformal blocks of LG hat, which were discovered by Igor Frankl and Nikolai Reshetkin in the 80s. So you can define them as correlation functions of chiral vertex operators, like in the conformal case, except that everything is Q deformed. Or, like in the conformal case, you can describe them as solutions to in this case, a difference equation, the quantum Canadian-xenological equation. So the quantum Aganagic homological equation is a regular difference equation which reduces in the limit to the Aganagic homological equation. So there's a way to go from this difference equation back to Aganagic homological equation in specific formula. So it turns out that the few conformal blocks of the quantum affine algebra have a geometric realization, and in some sense of the best possible kind, in that they come not just from some supersymmetric quantum field theory, they come from a gauge theory. And gauge theory is, in a sense, they're linear systems, right? So that's the best possible case. So so for now, let's take LG to be a simply Lacey algebra. So LG and G are the same, and it's of AD type. So the gauge theory we need is a three-dimensional quiver gauge theory with quiver based on the Lincoln diagram of G. The ranks of the vector spaces associated to each node of the quiver, the framing vector spaces and the gauge vector spaces, are determined by which conformal blocks you want to study. They are determined by the total representation and the weight and nu in that representation. Okay. So you get a quiver once you pick a fixed weight in the representation. Corresponding to that quiver is a quiver variety X, which actually entered the story of quantum affine algebras earlier in the work of Nakajima, who showed that the quantum affine algebra acts on the classical K theory of X. Now, Andre with Devesh and Andre Smiro, developed quantum K theory of Nakajima quiver varieties, such as X. And they showed an amazing fact that quantum K theory of the quiver variety, corresponding to this quiver, provides solutions of the QKZ equation of the quantum affine algebra. Not only does it provide it, but it provides it as one of the very basic objects of the theory. So one gets solutions of the QKZ equation as generating functions of equivariant K-theoretic counts of quasimaps from D to X, the Nakajima quiver variety, of all degrees. These generating functions where you sum up over maps of all degrees go under the name of K-theoretic vertex functions. So here you work equivariantly with respect to a torus that contains rotations of X that preserve the homomorphic symplectic form, and also importantly with rotations that scale the homomorphic symplectic form with parameter h bar. This h bar is the h bar in the quantum affine algebra, and also with respect to rotations of the domain curve. So for me, the domain curve is you can think of it as P1 with a puncture infinity, or this the longest way to get through it. So actually, these vertex functions also have a physical meaning as supersymmetric partition functions of a three-dimensional quiver gauge theory with the same quiver on D. D is the domain of quantum K theory times a circle.
And what you called H bar, is it the same as what you previously called Q?
Let's see. So I'm going to say it in a moment. So, so all the ingredients I'll have in the Q conformal block have a geometric and gauge theory interpretation. So the stat of the QKZ equation is parameter by which the disk rotates. So you rotate the disk as you go around the S1. The positions of vertex operators are equivariant parameters that preserve the holomorphic symplectic form of X. And you have as many vertex operator insertions as the total red of the framing spaces. And the parameter h bar in the quantum affine algebra is corresponds to scaling of the holomorphic simplex form.
So you had Q before. This was before.
Well, we
H,
say
right?
Q deformation, right? Aha, good.
Because
There's
you had
Q of the knot theory.
already before deformation.
There's a Q.
Which
This,
connected
That's
the level.
right.
it's related to both of them, and it will
But this
come back.
H bar is what is called Q in our
Yeah.
group,
So
right?
so basically, H bar and P encode the Q of knot theory plus one deformation parameter.
Right.
Like square was called Q.
All right. Yeah, and finally, the highest weight vector of the Verma module. Remember, I really get to pick one of them, and then the other one is determined by the weight I want to study. Is related to the degree counting parameter of quantum K theory in the following way. All right. So finally, the algebra itself, the quantum affine algebra, acts through on the vertex function through insertions of equivariant K theory classes at the origin of D. And the data and infinity determines which vertex function, which solution of QK's equation, and which vertex function you get. So really, this comes from a three-dimensional gauge theory. So the boundary is a torus, and this choice of boundary data means that you really should think of these K-theoretic vertex functions as being valued in equivariant with the homology of X. Okay. Now, while you get solutions of QK's equation from enumerative geometry in this way, it turns out that solutions you get are not really, while they're solutions of the same equation, they're not what you'd call Q-conformal blocks. And here's why. So, to get a Q-conformal block, remember, in constructing it, you perform some suing of vertex operators. So, by design, you get functions which are holomorphic in a chamber corresponding to a choice of ordering of vertex operators. Okay? And this choice is a choice of equivariant parameters of X. Now, so the solutions you get are not analytic in that chamber, in any particular chamber, in fact. Instead, they're analytic in a chamber of Kähler modulo X, which are related to a choice of, the choice of that chamber is a choice of, related to a choice of Verma module. They're analytic in terms of the Z variables simply because they come from enumerative geometry, and this keeps track of the degree.
But do they satisfy the dynamical equation which can
They actually satisfy two different equations. That's right. But the one that we'll focus on is the one in the A variables.
But they satisfy also the equation from my paper with Marsh.
Yes, they satisfy two sets of different equations. One with respect to the Z variables and one with respect to the A variables. That's right. All right. So, enumerative geometry of X does not provide us with the answer to the question we were after. Namely, the geometric interpretation of conformal blocks, even after deformation. However, it turns out that we are not far. Namely, this X, the Nakajima-Kuyo variety, is not the only geometry that underlies solutions of QK's equation. Of our QK's equation. Which QK's equation? Well, the one that came from the well, really, honestly, the representation theory problem we started with. So it turns out there's another geometry in the problem. So remember, X came from a 3D gauge theory. And it turns out that there is not one, but in fact two natural holomorphic symplectic variety that one can associate to the same 3D gauge theory with this amount of supersymmetry. So one variety is X, the Nakajima quiver variety, which a physicist would call the Higgs branch of vacuum of the 3D theory. The other one is the Coulomb branch, which appeared in Hiraka's talk this morning, and which we'll denote by X check. So for our gauge theory, the Coulomb branch X check is a certain intersection of slices in the thick affine Grassmannian of G. Here G is the adjoint form of a Lie group with Lie algebra G. There's another way of thinking about X check. So for general quivers of this type, you need some you need a certain generalized classes in affine Grassmannian. But for me, this weight nu is all the interesting cases correspond to essentially nu is equal to 0. So we really honestly get classes in affine Grassmannian. Anyway, another way of thinking about X check is as the moduli space of G monopoles on essentially on R3, where lambda that tells you which representation you're studying encodes the charge of singular monopoles, and which weight in that representation encodes the total monopole charge. So the positions of vertex operators. So these two different holomorphic symplectic varieties associated to the same gauge theory work as follows. The position of vertex operators, which were equivariant parameters of X, the Nakajima quiver variety and Higgs branch, become Kähler parameters of X check. And vice versa. Now, with Andre, we proved that that whenever it's defined, the K-theoretic vertex function of X check solves, in fact, the same QKZ equation as the vertex function of X. In fact, they solve the same pair of difference equations. Now, this is a consequence of three-dimensional mirror symmetry, which says that with suitable identification of parameters, which involves exchange of Kähler and equivariant parameters, and suitable identification of boundary conditions, the theory is based on X and X check, i.e. distinguishable. The choice of boundary condition enters into which solution of a difference equation you get. But which difference equation you solve treats X and X check.
What do you mean by the theory is based on X and X check? What does it mean by the theory is based on X?
Well, so here we study, if you study enumerative, a physicist will mean something fairly precise, right? Here you can just take it as enumerative geometry of X and X check, as in quantum K theory.
The quantum K theory.
So quantum K theory of this Coulomb branch, the quantum difference equation will be quantum K equation.
Yes. Really, what happens physically is that there is some three-dimensional conformal field theory that believes that really at the intersection of X and X check, and you'd use slightly different words to describe it depending on whether you pick X or X check, but it's the same theory.
The mathematical.
Yeah. So,
you're saying that
so here, so there is actually, what we show is actually stronger. There is a specific map of geometric question on X to a question on X check. Not just, so you can match not just the fact that they solve the same difference equation, but actually match solutions, right? And that's how this matching of solutions works is governed by something called the elliptic stable envelope that sort of gives that translates quite literally the geometry of one into the other. So we will not need that story here, so I will not describe it.
Do you actually do it in general or only type A?
Sorry?
Do you actually do it in general or only type A?
This works for completely general.
The notion of quasi-matrix, so one.
So for this, so here, the quivers are of type AD. The nodes on the quivers are always general linear groups. So that's the setting that we need. Right? So to the node, in principle, you could consider some funny quivers where the nodes are.
I'm talking about the quantum K theory.
No, but I think so. the statement we actually use is when we need the symplectic torus that have isolated fixed points on both sides, which is more general than type A, but it's
We can actually define quantum maps.
But then it's
something
smooth.
which is not equal to right.
no, but then it is okay. Then
You're right. That's right. So it's slightly bigger the generality than type A. You just need you need the extract to be self-equivalent.
Some of it is.
All right. Anyway,
no, the statement is abstract. I mean, just whenever you have a pair of varieties that both have isolated fixed points, and there's some matching between the fixed points, and in fact, the quantum equals.
So you do not obtain arbitrary quantum crazy equation, but only in minuscule modules, or what does it?
things are really nice for minuscule representations. But so why? Sorry,
So what is the precise answer to Sasha's question? In what generality quantum crazy equation can be rigorously interpreted as quantum differential equation of some geometric?
In the world where x and x check are smooth and you have isolated fixed points, you prove better.
But just in terms of, suppose I have quantum affine algebra and put some representation, write quantum crazy equations, what conditions should it satisfy to be a quantum connection of some well-defined problem?
Well, maybe I can ask you this question later.
This, to some extent, these are technical questions. There's no question that sort of physically the theory should make sense. The question is how to compute and how to define it.
Okay.
Anyway, so from perspective of x check, the QKZ equation is a quantum difference equation because it's a difference equation with respect to the A variables, and they're Kähler variables of x check. Okay, so this quantum difference equation is a K-theory analog of quantum differential equations of Gromov-Winter theory. Now, while the two vertex functions solve the same QKZ equation, they give two different bases of its solutions. So vertex functions of x will be analytic in the z variables, but not in the a variables, while vertex functions of x check will do the opposite. They'll be analytic in the a variables, but not in the z variables. All right. So, to summary, if you want to get Q-conformal blocks of the quantum affine algebra, you want to study vertex functions of x check, for which the a variables are Kähler moduli. All right. Now, the question we were really interested in is to find the geometric interpretation of conformal blocks of the affine algebra, not its Q deformation. Now, conformal limit is a precise limit that takes the quantum affine algebra, affine Lie algebra, while taking Q conformal blocks to conformal blocks. So it amounts to taking P, the step of the difference equation, to 1, H bar, the deformation parameter, to 1, keeping fixed kappa. So kappa is the level of the affine Lie algebra. While in addition, because the z variables are related to the weight of the Verma module like this, z variables also go to 1. But positions like kappa, a, and mu stay fixed.
So can't you just, instead of K-theory, take the homology, and wouldn't it give you
The
what
just
you want?
again. So now the conformal limit treats x and x check very differently because it treats z and the a variables differently. Okay. Z goes to 1 in the limit while a is fixed. So, from perspective of x, the Higgs branch, conformal limit is not geometric at all, because it gives you a very badly singular space, because in the limit, you're taking to 1 its Kähler variable. So any geometric interpretation in terms of x is gone. By contrast, from perspective of x check, things are wonderful. Its Kähler variables are the positions of vertex operators, and they're kept fixed. So, from perspective of x check, the conformal limit is simply the cohomological limit that takes the quantum K theory of x check to quantum cohomology of the same space. And the Knizhnik's homological equation that you get in the conformal limit becomes just the quantum differential equation of x check. So it follows that conformal blocks of the Lie algebra have geometric interpretation as cohomological vertex functions of X check computed by equivariant global width theory.
And by the way, this technical difficulty Sasha was talking about for cohomology, it doesn't happen, right?
That's right. So
Still have,
you still need X check to be
Yeah.
smooth, but
still may not have a single resolution.
So this is not the same difficulty which you get when you have T star of G mod V, when you have trouble defining quantum field theory. It's not the same.
you don't have a, before we needed to have a notion of quasi-math, which sort of required Gibbs theory description, or Nicodemus theory. Anyway. Okay, so, now, this cohomological vertex function is simply count the holomorphic maps from D to X check, working equivariantly. Now, the roles of equivariant and scalar parameters get switched between X and X check. So now equivariant parameters have to do with the choice of Riemann module, and also the scaling of the holomorphic symplectic form of X check. So the parameter that scales the holomorphic symplectic form is related to Q or kappa of the Lie algebra, and Q of knot theory. All right. Now the domain is, you should think of it as an infinite cigar with a circle boundary at infinity, and where the boundary data is a choice of equivariant K-theory class. Now, so why we were after this geometric interpretation of conformal blocks in terms of X check, because it's more than just the words of having associated Gromov-Witten theory to it. So it has far more information. So underlying Gromov-Witten theory of X check is a full two-dimensional supersymmetric sigma model with X check as a target space. And the physical meaning of the vertex function of Gromov-Witten is a partition function of a supersymmetric sigma model with target X check on D. So to get the vertex function, you do something slightly unusual. In the interior of D, you have an A-type twist, while at the boundary at infinity, you place a B-type boundary condition. So this B-type boundary condition is an object of a equivariant derived category of coherent sheaves on X check. The choice of which object of the category of coherent sheaves of X check which you associate to the boundary at infinity determines which conformal block of the Lie algebra the vertex function computes. It determines it, but of course this depends only on the K-theory class. So, now, since the Nijnich's logical equation solved by conformal blocks now has a geometric interpretation as the quantum differential equation of X check, the action of the UQ quantum group corresponding to a break on the space of conformal blocks now has a geometric interpretation as monodromy of the quantum differential equation along the path in the scalar modulo of X check. Thus, positions of vertex operators at scalar modulo. So the monodromy acts on the vertex function by its action on K-theory classes associated with boundary at infinity. It just mixes up solutions of the differential equation. So hence it's associated with boundary at infinity. Now, by cutting and gluing, by cutting the vertex function somewhere into pieces like this, breaking it up, it follows that the matrix elements of monodromy matrix are annulus amplitudes of the now B-twisted sigma model to X check with a pair of B branes at a boundary. You could take a full supersymmetric sigma model, but because the boundary conditions preserve B-type supersymmetry, now this is just you could just as well work in the B model. So the B model annulus amplitude, essentially per definition, is a supertrace over the graded home space between the two branes computed in the derived category of T equivariant coherent sheaves on XCheck. So if you just ask what contributes to the annulus, the answer is this. So this is essentially a physics retelling of the theorem of Roman and Andre, which says that action of grading matrix on the equivariant K theory of XCheck by monodromies of the quantum differential equation lifts the derived autoequivalence functors of the derived category of T equivariant coherent sheaves.
Our theorem is a lot less general than what you.
Okay, well you need to write it up.
Sorry, yeah.
Sorry,
This is for the future.
Okay.
And
You're getting so much homework in your birthday, it's really awful. Complain.
and the autoequivalence on DB Koch should be in characteristic P. Is that no?
This is characteristic zero based on this. Well, switch to large P based on.
No, but don't you get for characteristic P an additional parameter, which is
So
the
you
grading?
construct them through characteristic P, but they are removed from characteristic P.
But in characteristic P there is a grading, which gives you an extra
No, but the
parameter,
grading
no?
here is just the grading by the reaction of it.
It's in characteristic zero. Uses characteristic, just as on basic.
Now, this also implies that categorification of invariants of quantum link invariants comes from the derived category of coherent sheaves, because link invariants can be expressed as matrix elements of the braiding matrix between pairs of conformal blocks. So, denote by F in and F out, branes that give rise to the top and the bottom conformal blocks, and like this, the image of F in under the braiding functor. Then the corresponding categorified link invariant is the graded home between the branes computed in the equivariant derived category. So in addition to a homological grade, there is at least one more grade coming from the torus action that scales the holomorphic symplectic form on XCheck with a weight Q. It's not entirely obvious from this prescription that for conformal that other ways don't enter, but they should.
Why are these called brains?
Huh?
Why are these called brains?
So by now I think it's standard in wider, not just physics community, but wider mirror-symmetry community to call objects of derived categories of coherent sheaves brains, and they call them
Really?
Well, okay, maybe it depends whom you talk to. At Berkeley, it's certainly standard. I think in the math department.
Physics definition was that general.
Now, the three-dimensional gauge theory that we started with actually gives us a second description of categorified link invariants. So it leaves a description in terms of a two-dimensional equivariant mirror of XCheck. So the equivariant mirror is a Landau-Gisbert theory. So it's defined by the target, which is Calabi-Yau, and then the potential W. So the Landau-Gisbert potential, in fact, both the target and the potential you can derive from the 3D gauge theory. So in other words, essentially once you have the quiver, you have both. One sort of way of getting at it, which is somewhat roundabout, but still instructive, is as follows. So recall that in conformal limit, where the quantum affine algebra becomes ordinary Lie algebra, the K-theoretic vertex function of X has no geometric interpretation in terms of X anymore, because X is singular. Now, while it doesn't have any interpretation in terms of X, it has to have some limit. Because solutions of equations don't just disappear. To find it, it's useful to use to be able to take the limit, you don't want to think of this in terms of counting quasi-maps. But if you think of it, it has an integral formulation that we discovered, don't we? It's
like in the spell.
Oh, I'm so sorry. Oh yeah, I apologize. Fortunately, you're so famous that everybody knows what I meant. Okay. All right. So these integrals, they come about.
Yes.
So they come about by thinking of quasi-maps to X in geometric invariant theory terms. So you think of them as maps to the pre-quotient, and then projecting to gauge invariant configurations, you integrate over the maximal torus of the gauge group. So this integration of the maximal torus is what gives you the integrals. And the maps to the pre-quotient give you the integram. So in the conformal limit, the conformal limit of the vertex function of X has the following form. And it gives integral solutions to the Aganagic equation corresponding to the conformal blocks we started off with. Now, the function W that enters is the Landau-Gisbrook, that enters this formula is the Landau-Gisbrook potential, and omega is the top holomorphic form in Y. And then it is a top holomorphic form in Y. Now, anyway, so the integral is over Lagrangian in the target space of the Landau-Gisbrook. So what we are discovering here is integral representations of conformal blocks of the affine Lie algebra. They go back to works of Frankel and Fagan and Sheckman and Bartikov. But now we are rediscovering them from supersymmetric quantum field theory and from geometry. Now, the fact that the Knischig's homological equation, which the Landau-Gisbrook integral solves, is also the quantum differential equation of X check, gives a given style proof of two-dimensional mirror symmetry, relating equivariant A model on X check and B model on Y with superpotential W.
But you need to represent some theory as gauge theory to get this integral representation.
Huh?
Like for example, for T star of G mod B, you cannot have integral.
That's right. I have to start with a gauge theory. And fortunately here we do, for a reason that's somehow miraculous, but we'll see why. Now, the Landau-Gisbrook origin of conformal blocks automatically also leads to categorification of the corresponding Braidon invariants. So, from Landau-Gisbrook perspective, the conformal blocks are partition functions of the B-twisted theory on an infinitely long CR, where the B-twist is in the interior, and at the boundary at infinity, we impose an A-type boundary condition, corresponding to a choice of Lagrangian in Buchardt. So, solutions of Knischig's homological equation from this perspective come from choices of A-branes, which are objects in Landau-Gisbrook theory, which are objects of a higher category of A-branes on Y with potential W. The corresponding categorified link invariant would then arise would arise as Floer's homology groups, which are now bi-graded. The second grading comes from what I flashed a little bit too fast, from the winding number. The reason you get a winding number is that this potential is not single. The potential W of the Landau-Gisbrook model is not single valued. These kind of non-single valued potentials are a hallmark of equivariant mirror symmetry. All right. So but then we get a two-dimensional equivariant mirror description based on proprietorial category of Y and W.
So
Yeah.
do you get new proof of the Barchenko-Sheckman integral formulas for solutions using this? They have very specific formulas for any
if you start,
that's Moody algebra basically.
if you start with our formulas for first the elliptic stable envelopes and then corresponding the K-theoretic limit, you would get exactly the formulas, integral formulas for that.
No,
So in
the question is, can you actually do the computation and get exactly the same, like a proof of that formula?
I didn't try to actually prove it, but you can show that. I'm sure you could actually do it.
What generality are they from?
Formulas are completely general for any.
Yeah, so this is not as general as that. So you need at least like fundamental vertex operators which come from fundamental representations.
You need minuscule representations.
No.
No, not minuscule.
This is a arbitrary product of the
Okay. Well, that's general enough. So you can obtain, because the question is how explicit you can go with this thing. I understand in principle you can go very explicit, but for example, in the cutiform case, the formula isn't known. I mean, it's known.
Yeah,
it's
the
expected
cutiform
that
case
they
is
exist.
much more information than this conformal limit.
So because representations are not just evaluation, but they're some more complicated, there isn't, it's not even known how to write this formula in some elementary way, in general. Even for fundamental representation.
No, for tensor product and number representation, there is absolutely general formula. I mean, it's slightly what is somewhat not so explicit is the cycle. The cycle comes from general description that this any sort of integral which I take quotient is an integral over a cycle which we get from some very theory. Maybe not very explicit cycle, but for tensor product, this is very general. It doesn't have to be a fine dimensional unit. It can be any fluid. As long as you have that product relation representation, there's a focus for such.
What do you mean by evaluation? Fundamental.
Fundamental.
But fundamental representations are pretty complicated already.
Yes,
for
whatever,
outside of type A.
Yes.
And you have to have some basis for them to write anything.
No, I mean this fundamental. No, I mean this it's.
So the final formula you get, is it purely combinatorial or analytic, or does it still have some geometric pieces in it?
There's a way to write. So if you think of K-theory of some space, there's a way to realize that as function satisfying such and such conditions, if you integrate this sort of functions over some cycle, which the cycle is again both what sort of function space you consider and what sort of cycle of integration. This is gotten from slightly absolute truth.
But the answer is completely explicit.
The answer is explicit to the degree that you can say something explicit about like a G program.
So it turns out that there's a third approach, which is related to the first two I described. It's important to, even though it's slightly more difficult, it's important to understand the connection, because what it does give is a unified picture of approaches to not categorification problem where it comes from. So it will also demystify sort of a strange aspect of the story. For a very long time, people knew that somehow three-dimensional gauge theory should have something to do with categorification of multivariates. Maybe the Coulomb branch, maybe the Higgs branch, and so the question is, what do three-dimensional gauge theories have to do with multivariates? So the explanation comes from string theory. So more precisely, it comes from six-dimensional little string theory, which so these are labeled by choice of a simply laced Lie algebra, so they come in AD types. You can think of it as well, it's obtained by starting with type 2b string theory on an AD singularity of type G. That's where the choice of AD comes from. And taking the limit where you only keep the degrees of freedom at a singularity. So type 2b.
Is it times R2? I mean,
Well, type 2b string theory starts in 10 dimensions. So 4 of the dimensions come from the AD surface, and you're left with 6. So these 6 gives you the little string theory. So you keep the string theory that's located at a singularity. So the Q-conformal blocks can be understood as supersymmetric partition functions of G-type little string theory with D-branes. So you want to take this 6-dimensional string on a manifold that is a product of the Riemann surface A, where the conformal blocks live, essentially direct product. D, the domain curve of where our 2-dimensional theories that arise so far live, and then an auxiliary complex plane. So those are my 6 dimensions. The vertex operators come from a collection of defects in little string theory that are inserted exactly where the vertex operators are. So these D-branes that one needs are 2-dimensional defects that are supported at points on the Riemann surface, as I said. They're supported on D, and then at the origin of this extra complex plane. There's an implicit sort of equivariant rotation of this extra complex plane, so it's really boring in that everything has to sit just at the origin to preserve the rotation symmetry. Anyhow, so the choice of which conformal blocks to study comes from choices of which D-branes. Now, the theory on D-branes in string theory is a gauge theory. The fact that theories on D-branes are gauge theories, and in fact, it's the same quiver gauge theory that arose earlier in this talk. So this is a consequence of a sort of familiar description of D-branes and AD singularities. It goes back to work of Douglas and Moore in 1996, which came about by them trying to understand how Hiraku's work fits into string theory. So it's a very old story. So the theory on D-branes supported on D turns out to be a 3-dimensional gauge theory on D times S1 because of a stringy effect, because you're studying string theory. So because the target is a Riemann surface, which is an infinite cylinder, the winding modes of strings that wind around and begin and end on the defect, which you have to take into account. And those turn a 2-dimensional theory on D into a 3-dimensional theory on D times S1. Anyway, now conformal limit turns out to be a point particle limit of little string theory. So in the limit where you turn off the Q deformation, you get a theory with extra conformal symmetry on it. It turns out the 6-dimensional theory, which has broken scale invariance, broken by the string scale, becomes itself conformal. So the 2-dimensional and 6-dimensional conformal limit are the same limit. And because you're taking a point particle limit, winding modes become really heavy. So the winding mode that made defects at points on A get another dimension go away, and the theory on the defects becomes purely a 2-dimensional theory. The infinite power of winding modes goes away. Anyway, so this 2-dimensional theory on defects, or the 6-dimensional 2-0 theory, is quite a bit harder to understand than simply gauge theories on D-branes, because it's not a gauge theory, but it has 2 descriptions. One in terms of a sigma model to X check, the Coulomb branch, or the other one in terms of a Landau-Ginzburg model in D with potential W. So both of these approaches started with theories on the knots. The third description, due to Witten, starts actually from the perspective of the 6-dimensional theory in the bulk. So the 6-dimensional conformal theory, or 6-dimensional little string in the bulk, is quite difficult to understand. But once you compactify the 6-dimensional conformal theory on a small circle, it becomes a gauge theory, ordinary gauge theory, with gauge group G in 1 fewer dimensions. So, to get a good description of the problem, what Witten does is he shrinks a circle that's you can associate to rotations of this extra auxiliary complex plane. So from a 6-dimensional theory on this nice manifold, you get a 5-dimensional gauge theory. Because the circle is contractible, you get a 5-dimensional gauge theory on a manifold with a boundary. The boundary is where the circle shrinks. So the total space is domain where the two-dimensional defects live, the Riemann surface where the Coulomb field lives, times a half-life. That's the 5 dimensions. And the theory in the bulk has gauge group G, which is the adjoint form of a Lie group with Lie algebra G. Moreover, the two-dimensional defects that gave rise to our vertex operator are monopoles of this 5-dimensional gauge theory. They are supported on D and codimension 3 in this space. And they live along the boundary of this three-manifold Lie boundary. Now, what Witten shows is that the 5-dimensional gauge theory on this manifold with the boundary and a specific boundary condition, which you derive coming from 6 dimensions, can in fact itself be viewed as a Landau-Ginzburg model on D, but now with an infinite dimensional target. The fact that you have all these the 3 extra dimensions means that the target of Landau-Ginzburg is a space of GC connections on M3, and the theory has a potential which is given by the transsinus function of. Moreover, the boundary conditions that you impose here depend on the knots, because the knots are located at the boundary. But anyway, to obtain non-homologic groups in this approach, you end up counting, so you do sort of a 5-dimensional, instead of doing a 2-dimensional Fukaya-Seidel theory, you do a 5-dimensional Fukaya-Seidel theory. So instead of instanton equations being 2-dimensional equations, they become 5-dimensional equations. So you basically end up constructing, to construct a differential, you count solutions of some 5-dimensional equations that let you construct Floerke homology groups of this 5D line of All right. Okay. So that we end up with 3 different approaches to the non-categorification problem with the same 6-dimensional origin. Okay, so since I'm over time, I'll say a few words. Yeah, so they're all describing the same physics, just from different perspectives. Witten's perspective describes the entire 5 or 6-dimensional bulk. This geometric perspective, based on 2-dimensional theories, describes the theories on the knots themselves, so the perspective of the defect. Okay. Now, the approach based on derived category of T-equivariant coherent sheaves on X check in type A is equivalent to that of Cummins and Couch's. The approach based on Fukaya-Seidel category of Y and W is related to the approach of Seidel and Smith for A1. So Seidel and Smith's work, it actually preceded Cummins and Couch's. So they use Fukaya category of ordinary mirror of X check in the A1 case to construct what they call symplectic covenant homology. Now, symplectic covenant homology is a singly graded homology theory. So it's a specialization of covenant homology to Q is equal to 1. But to obtain it, you only need to, there's no potential. You just deal with Fukaya categories of the mirror of X check. The approach that we have includes the grading from the outside, because it's essentially what gives rise to the potential, and it works for any LG. Okay. So in general, I think this mirror symmetry that relates the equivariant mirror symmetry that relates X check to Y and W should be a very useful tool in representation theory and also category theory. It's a little bit subtle, for the reason that Y is actually half the dimension of X. So what Y is mirrored to not equivariantly is not actually all of X, it's its core locus. So it's mirrored to the locus of X that corresponds to fixed points of this action that give you the Q variable. Okay, that half the dimension of the space. And Y is, so Y is an ordinary mirror of sort of half of X, the core of X. But since you need to work equivariantly anyhow for the non-theory problem at hand, it's very compact and encodes all the information you need. Anyway, so the question which categories one should study gets training for more focused questions like understanding the geometry of objects in these categories that correspond to caps and caps, that map to themselves under the functors corresponding to half twists, and whose cell cones categorify quantum dimensions. So for groups of A type, it's not difficult to see what caps and caps should be, right? They're essentially Grassmannians. But more generally, I think it becomes a story that's really concrete and very interesting to work out. Okay, so this has extensions to non-simple lattice cases, which I would have told you about had I not been out of time, and would have tied in very nicely to hear out this talk, but some other time. All right, thank you.
I believe we have time for maybe 2 quick questions. Any questions?
Yes.
W algebra conformal blocks. Here,
Yes.
or Q4.
Right. So basically, the relation between double algebra and unfinally algebra conformal blocks in the end is some simple question of a choice of a boundary condition at a time, right? So yeah, in some sense they are also there. In other words, braiding of double algebra conformal blocks is the same as the braiding of the unfinally algebra conformal blocks. So you could have used them as well.
The Landau-Ginzburg integrals that you wrote, they look more like, they seem to look more like double algebra conformal blocks. Because the scale,
Not really. Well, okay. So you can trade vector solution of a linear differential equation for scalar solutions of a high order differential equation. But
that's more or less what trades.
yes, that's right.
Conformal blocks for double algebra.
That's right. You could do that as well.
To me, the formulas you wrote look like more like the double algebra conformal blocks.
You could, but there's a supply of insertions that could. I mean, there's the story of mirror symmetry theory. That's sort of one. Yeah, double algebra conformal blocks happen when you put a trivial insertion at the origin. To get the quasi-conformal blocks, you need some very special other kinds of insertions if you want to get it in the canonical case. Okay. All right.
But you showed that they're equivalent.
Yes, absolutely. What's for example striking in typical stories of mirror symmetry, understanding the flat coordinate in which the B model reproduces the A model is an extremely difficult problem. Here, the solution to this problem is canonical. The flat coordinates are the positions of vertex operators. It's kind of an amazing fact. So it's a place where at least ordinary mirror symmetry has essentially been solved. So I think it's interesting for many reasons: geometry, representation theory, and in the end, categorification as well.
Maybe one more quick question.
How about the quick statement? that this realizing Kz as a quantum differential equation is a problem which many people work. I think Vanya Pimenko over there has the best theory. I don't know if there was a reference missing in our
there's a reference is missing. This is work. To which
What is the theorem?
yeah. To actually prove.
You're going. There's a little bit of a break remaining.
Yeah, so maybe a subsequent discussion should be postponed for a coffee break, which will be after the next talk. And the next talk will be at 3:05. And that's going to be 5 minutes. The break collapsed to 7 minutes, yes.